Hello again, class. Welcome to week 4. This is the continuation of your video presentation on the lectures regarding inferential statistics. The last video we were talking about z-scores, we're talking about probabilities, and we were also talking about hypothesis testing. Now let's move on to one of the most commonly used inferential test statistics, and that is your t-test. Now there are three types of t-tests. The first one is one sample t-test. This test statistics is used to compare a sample mean with a known population mean or some other meaningful fixed value. Simply put, you have a known population, for example, the class of 2015 taking the National Collegiate Entrance Examination, and your question is whether this sample, which is just one sample, whether the mean is the same, which is your null hypothesis, with whether the mean of the NCEE score is the same when compared to the mean of a known population. So that is one example of a one sample t-test. Again, this is a very specific t-test that is used to compare a sample mean. For example, again, as I've mentioned, the class of 2015 taking the National Collegiate Entrance Examination. So you're going to get the sample mean of that particular sample, and then you are going to compare that with a known population mean, which is for example in this case will be the population mean of all the graduating high school students in the past. So you know already what was the mean, what was the standard deviation of past high school students taking the National Collegiate Entrance Examination. I think that it's no longer called NCEE nowadays in the Philippines. They told me that there's some other names, but I graduated way back in 1987. It was called NCEE. So again, when you do one sample t-test, you're comparing your sample mean with a known population mean. So that is where the quickest example I can think of is the sample mean. If you're going to take the mean of the class of 2015 and then you compare that to some other meaningful fixed value such as of a known population, such as all of the previous mean of the high school graduate taking the National Collegiate Entrance Examination. So that is an example of one sample t-test. You have to remember there is a known population mean all with a known standard deviation as well. Let's move on to the second type of t-test, that is your independent samples t-test. Well, from this from the name of the test alone, you already know that it has two different samples because it says independent samples. So you have two samples and you are still using the t statistics, and what this means is that you're going to use this statistics to compare a sample mean with a known population mean or some other meaningful fixed value. However, you have two independent samples, not just one. In my first example, you only have one sample because it was just the cohort of the class of 2015 taking the National Collegiate Entrance Examination. Now, if you're going to do independent sample t-test, then you need to have two samples. So it could be then the class of 2015, and then you have another sample, the class of 2014, and then you're going to compare the sample mean with a known population mean, and you create your hypothesis, your null hypothesis. And depending on your t-test statistics, you are going to reject or accept your null hypothesis. What about the third type? Well, the third type is called the paired or dependent samples t-test. This time, from the word itself, paired, so this is now a t-test statistics that is used to compare the two means that are repeated measures for the same participant scores. An example for this would be your paired t-test, such as in your pre and post test research design. So you're going to develop an educational intervention, and then before you implement your educational intervention, you're going to take the mean score of the knowledge of your sample, and then after you delivered your educational intervention, you're going to repeat the same exam or measure to the same participants, and then you will pair them directly, which means that the score of participant number 1 will be paired exactly to the score of participant number 1 post intervention. So pre and post intervention, you need to pair them, and that is what you call the paired samples t-test. Now, I get a lot of questions in the past that is it still legitimate if you are unable to pair the scores of your participants in a pre and post test research design? Well, the answer is no. You really need to make sure that you have your code. For example, if your participant number 1 is Joseph Terriman, and then your participant number 2 is Barack Obama, then you need to make sure that you have your code correctly, and that when you put your scores into SPSS, you have to make sure that my pre-test and my post-test score is definitely paired, and that the pre-test and post-test scores of Barack Obama is also paired. Now, when you put it on SPSS, you don't put the name of your participants, you actually just put numbers, and that's why you need to have a code book. And that is an important thing to do when you do your paired or dependent samples t-test. So why do we need to do t-test? Why not stick to the z-scores? We've learned the z-scores already. We're able to standardize the distribution with the z-scores, and we're able to make meaningful interpretation of individual scores, because now we're able to standardize the distribution, and we can make meaningful interpretation of where an individual score stands in relation to the sample mean. Well, the problem with the z-score is that it requires more information than the researchers typically have available. As I mentioned, I think in the last video, z-scores, in order to determine your z-scores, remember the formula of the z-scores? The formula of the z-scores is that it has the mean of the individual, or the sample mean, minus the known mean of the population, divided by the sigma, or the standard deviation, and that's also a known standard deviation. Well, what happens then if you don't have the standard deviation of the population? Well, you won't be able to use the z-score. So researchers usually have only the sample data available in some research. So you cannot use z-scores. As what I mentioned, I think the last with the last video, is that there are times when you do your research and there were no previous study related to your research interest or your topic of interest, and therefore you really have no known mean or no known standard deviation for your research or topic of interest. Well, in that situation, you cannot use z-scores, because z-scores require that you know that you have a known mean and you also have a known standard deviation. So here comes t-test. So what is the history of t-test? Well, actually it's all about the beer. Not all about the base, but it's all about the beer. Beer, like we all love beers. Like we love to drink beer. So what's the history of the t-test? Well, in early 1900s, Guinness, which is your Guinness beer, and also the very famous for Guinness World Book of Records, and I will never forget Guinness because I've been to Ireland, and the headquarter of Guinness beer, of course, is in Ireland, and they give you free sampling of beer. Anyway, I digress. So back to the story here. So Guinness began recruiting scientists as masters brewer to apply scientific methods to beer production. They wanted to have a competitive edge. In Europe, beer making, especially the Germans and also the Czechs and almost every country in Europe, they love to make beers. And so the competition is very, very stiff. And so Guinness decided to recruit scientists as master brewers, and that they really want to have a scientific methods to monitor how they're being productive, to monitor standards, whether the standards of brewing beers were met, and they put all their ingredients into writing, just like any scientific studies. Everything has to be documented. Their ingredients included water straight from the Wicklow Mountains, hops, yeast, of course, and the barley that gives the and of course the barley, which is so important ingredient of the beer, because it gives Guinness its rich, distinctive color and taste. So one of the scientists that has been recruited as master brewer was William Seeley Gosset. He was tasked in studying and testing the essential ingredients to ensure that every pint was brewed to perfection. However, back in his days, statistical tests for average were traditionally conducted using large sample sizes. But that is so expensive, it's not cost effective, and so Gosset actually looked for other statistical methods using a small sample size. Gosset recognized that statistical methods based on large sample would not work in case of small ones. Like, he wanted to make sure that the quality of different batches of beer were maintained or strictly maintained. And so what would a statistician do if you can't find a statistical method to effectively analyze a small sample size with their mean? Well, of course, you have to make one. So that's what happened, and that's the birth of the t-tests. And continuing on with this history, Guinness understandably didn't want the competitors to know that they are now doing scientific inquiry in making sure that the quality of their beer is maintained, and that they also know the exact ingredients for every beer were followed. And so what they have done is that they kept this whole new statistical method secret, and when they actually published their findings, instead of using their own name, they used the pen name student. And so Gosset actually did not publish his name as Seeley Gosset, but rather he used the pen name student, and that's why you will also hear that the t-test is also called the student t-test. So after that brief review of the history of t-test, let's take a look at again what is one sample t-test. The one sample t statistics uses this estimated standard error in place of the standard deviation. So remember that in z-score they use standard deviation, and the standard deviation actually measures the variability of the scores, where what happens in t-statistics is that the variability of the sample means is measured by the standard deviation of the sample scores, called the standard error, and this is noted by sigma with an M. And the t-test statistics is typically used to test hypotheses about an unknown population mean, which is represented by your mu, when the value of the sigma, the population standard deviation, is also unknown, with a caveat that in the t-test statistics it is the standard error that's being utilized, not the standard deviation. So what is this, an estimated standard error? Why is this so important in the concept of t-test, or one sample t-test? Well, it actually uses the square root of the standard error to estimate the square root of the standard deviation. So an estimated standard error equals the standard error mean equals this equals the standard error divided by the square root of the sample, or otherwise also stated as the square root of the square of the standard error divided by the n. This again, the standard error is used to estimate the real standard error when the value of the sigma is unknown. So what's the difference between z-score distribution from the t-distribution? Because you have to remember that the t-test still uses the mean, and that is again a very important parameter. And every time you use the mean, you actually have an assumption that because of that feature, that there is a known mean, and therefore there is an assumption that the data, or the sample data, will be normally distributed. Well, what happens in a t-distribution is that the t-distribution approximates the shape of the normal distribution. So again, the key word there, it approximates the shape of the normal distribution. It is flatter than the normal distribution, a little bit more spread out than the normal distribution, and more variability as well in t-distribution. Now this is very key, because when you do your t-test, it's really for small sample. So you have to remember that the variability, there has to be a wider variability in order to detect that significant difference, or what we call the noticeably difference in the mean. So you will see that the t-distribution, the feature of the t-distribution is that there's more variability, and it has also a fatter tails. You can, just like your z-scores, we actually have the table of values for t also in place of the unit normal table for hypothesis testing. So you can use the table of values that's in the back of the book of a lot of biostatistics book, but with the computer nowadays you actually don't need to do that. Now when we discuss t-tests, it's inherent that we also understand what degrees of freedom is all about. Degrees of freedom is the computation of sample variance that requires computation of the sample mean first. In other words, only n-1 scores in a sample are independent. The researchers call the n-1 the degrees of freedom. And degrees of freedom is noted as df equals n-1. So when you, n means the sample, minus 1, so you need to know how many participants do you have, what's your sample size, that's your n, your actual sample size, and then minus 1, and that becomes your degree of freedom. So the null hypothesis for one sample t-test is expressed as follows. The t-statistics equals the sample mean minus the population mean divided by the estimated standard error. And that this is equal to the mean of your population mean when it's divided by your standard error, and that is that there is no difference between the mean of your sample mean when compared to the population mean. So that is your null hypothesis. There is no difference between the sample mean and the population mean. There are 4 steps for hypothesis testing using your t-test statistics. And number 1, you state the null and the alternative hypothesis. We discussed last time what is a null hypothesis and what is alternative hypothesis. Alternative hypothesis basically is you're stating that there is a difference, statistically significant difference. There is a difference between the sample mean and the population mean, or that there is an association, because your null hypothesis says there is no difference in the sample mean when compared to the population mean, or that there is no association between the variables of interest. Always remember that in t-tests you are comparing 2 means all the time. So again, that's an important concept. In t-test you are comparing means, 2 means all the time. It's a sample mean and the other one is a population mean. And when you look at SPSS later on, when you're trying to do t-test, what the command for SPSS looks like is simply you go to compare means, because that's what t-test is all about. It's really comparing the means, and I'll demonstrate that to you in another video when I'm going to show you on how to run SPSS on t-test and other common statistical tests. The second step of your hypothesis testing will be to locate the critical region using the t-distribution this time, and of course the degree of freedom. And remember, the degree of freedom is simply stated as n-1. So what is your sample size? That's your n minus 1, and that is your degree of freedom. Number 3 is the third step is to calculate the t-test statistics. Nowadays, we don't do this by hand. It's the 21st century, so you need to have your SPSS. And then number 4, you make a decision regarding your null hypothesis, whether you're going to accept or reject your null hypothesis. And again, the null hypothesis simply states that there is no difference between the sample mean and the population mean. So here is a good graph showing you, I think I've shown you the graph of the critical region for z-scores. Remember, it was plus 1.96 and then minus 1.96 on the negative side. That was for the z-score. Those were the critical region at an alpha of 0.05. Well, here you need to remember the concept of degrees of freedom. It's inherently attached to your alpha level and when you calculate the critical region of your t-test statistics. So if you set your critical region at in the t distribution at an alpha level of 0.05, you need to add what is your degree of freedom. So you need to know what is your sample size, what's your n minus 1. And for this particular graph here, the example here is that we have 9. We have an n of 9, so 9 n minus 1 is equals to 8. And so if you look at if you have a table or if you have a statistics book right now, you can actually go at the back of the book and you'll look at the t distribution. This is exactly what you're going to get, is that you need to reject your null hypothesis if the value of your t statistics falls above 2.306, that's a plus, or it falls below minus 2.306. So you have to remember in a distribution that both sides are equal. That's another concept that I've talked to you in the previous presentation, that in a distribution the two sides are equal. So you have minus 2.306 on the left and you have plus 2.306 on the right, and those are your critical region. And if the value of your t-test statistics will fall in this region, you need to reject the null hypothesis, which means that there is a statistically significant difference in your sample mean when compared to the mean of your population. Now if it doesn't fall, if your test statistics value is within minus 2.306 to plus 2.306, so that is an area where you're going to fail to reject your null hypothesis, and therefore you're going to take or accept the alternative hypothesis. So again, if it's beyond plus 2.306 or below minus 2.306, that's your critical region. You're going to reject the null hypothesis. For this particular example, this is for a sample with sample of 9, that's an n of 9 minus 1, so you have a degrees of freedom of 8. And the previous slide actually shows you that it's a two-tailed. That's why you can either go to the right or to the left. That was a two-tailed test. And you always do two-tailed test if you do not know, if you are not 100% sure on the direction of your experiment, whether it can go positive or it can go negative. If you do not know, then you need to do two-tailed tests, because you certainly don't want to miss out a negative direction of your experiment. What about if you're already you're 100% sure that the direction will be a positive direction? Then you can actually use one-tailed test, and that is towards the direction to the right because you said that the direction is going to be positive. And so the in this the same example with a degree of freedom of 8, then the critical region of your t distribution is actually at 1.86. Very different when you do your two tailed test because it's plus 2.306, and here it's only the t test value is 1.860, and then you look at the table and you need to look at what is the value for this particular t-test statistics with a degrees of freedom of 8. When you do SPSS, you don't need to look at the table. You don't need a ruler to make sure you're aligned properly with the degrees of freedom and the t-test value. You just simply need to really know how to use SPSS. So what are the assumptions of the t-test? Well, number one, that the values in the sample are independent observations. So that is key. So for example, if you have one sample t-test and that the score of the NCEE are definitely independent observations. So that means that basically, you know, the students are not copying and that they truly are values that are independent from each other, that nobody's giving them the same answer and then putting and getting the same values or score. So again, that's just a very simplistic way of saying in order to be independent, then there should be no manipulation of all of your sample or your participants, and no manipulations in terms of how you came up with the values or the data. So independent observation is a very important assumption of the t-test. The second assumption is that the dependent variable must be measured on an interval or ratio scale. So remember that you're not supposed to use t-tests if you are using ordinal data. And remember that ordinal data are typically those data that we obtain based on someone's judgment, someone's personal perception or values, and those are typically from surveys. Surveys that will ask you, do you agree, do you disagree, are you neutral, strongly disagree, and disagree. Well, those are all ordinal data, so you are not supposed to use t-test for those type of data because those are ordinal value, and t-test clearly says that the assumption is that the dependent variable must be measured on an interval or ratio scale. The third assumption of the t-test is that the population sampled is normal. So there has to be an assumption by the researcher that the population you're being sampled, that where you draw your sample, has a normal distribution. And with large sample though, this assumption can be violated because remember, as you increase the number of sample, what happens to the variance? It gets smaller and smaller, and the population mean tends to become similar with the sample mean, and that is a violation of the t-test assumption. So that is why t-test is very good only if you are conducting experiment or test with a sample of 30 or less. Again, I will repeat that. T-test is indicated for studies, experiments, if your sample size is 30 or less. Because once your sample becomes larger and larger, then it has the tendency to really create a problem, and then it will violate the third assumption of the t-test, that the population sampled is normal. And what happens when there's a large sample size? Well, basically it's automatic that there will be a normal distribution. So again, this is a very important concept when you do t-test. The sample, the n should be 30 or less. If it's above that, you need to go to other test statistics. You can do chi-square, you can do other things, but t-test is only good for an n of 30 or less. And I cannot overemphasize this. You cannot do t-test on ordinal data, and those ordinal data are very typical for studies using surveys. Anything that asks the opinion, the judgment, the values, the perception of the person, those are all ordinal data, because we cannot guarantee, the researcher and the participants cannot guarantee that the distance between the values are exactly the same. And that's what happens when you throw a survey that asks opinions, values, judgment, perceptions, preferences. So do not use t-test when you are when your dependent variable is using those type of scale. I'm going to skip the learning check here because those are very self-explanatory. Let's proceed to two independent sample t-tests. Two independent samples, it's plural. So two independent samples t-test. Now this time, from the word two independent samples, so these are two groups that are unrelated, and you are now testing the differences between the two unrelated groups, or what we call the independent samples. You can have an intervention group and a non-matched comparison group. You can also have males and females. Those are two groups that are unrelated. You could also have groups with and without medical condition. You can do that, but remember, this is a t-test, and the rule in t-test, it's good for samples that are 30 or less, because you're going to violate the third assumption of the t-test, which says that the population has a normal distribution. So what are you going to do if you have an n greater than 30? Well, there are many other test statistics that you can use. You can use chi-square statistics to check for statistical differences between two independent groups, and that is your males or females. For example, what is the cholesterol for males and females? And then if you have a sample that's 1,000, now obviously you're not going to use t-test for that. You're going to use other test statistics because your sample size is very large. So in order to test the mean, or you may say median, because that's for Mann-Whitney U test, you are going to basically use independent t-test if you're using the mean, and that is what we call the parametric. And parametric, from the word parameter, that is the feature or characteristic of your variables, and that is a parametric test when you do an independent samples t-test, and it uses the mean. Well, what happens then if it's a non-parametric test statistics that you would like to use? Well, it will use the median, and an example for that is your Mann-Whitney U test. So again, independent samples t-test, it tests or compare the two means, and that is parametric. Whereas your Mann-Whitney U test is non-parametric, and it will test or compare the median of your two independent samples. Let's move on to grouping variables, and again, I think it's easy to explain this when we go to the different examples. Examples are nominal and dichotomous variables, such as two categories. It defines the two groups being compared. It is usually, but not always, the independent variable. So examples of grouping variables are your gender, male versus female, immunization status, immunized versus non-immunized. There are so many grouping variables that you can do when you are studying or when you are trying to compare the means of two independent samples. For example, you can say college educated, non-college educated. So you could start collecting data, basically including those who only have grade school education, and then those who have high school education, those who have at least college level education all the way to doctoral degree. But then once you want to group your variable into only dichotomous variable, then you can just look at your sample characteristics and you create a cutoff, and then you say I'm going to group my variable into two dichotomous group. And if you're talking about educational level, then you're just going to say college educated versus non-college educated. So you're going to count everybody who had grade school and high school and vocational as non-college educated, and those with college education all the way to a doctoral degree as college educated group. So again, that is an example of how do you do grouping of variables. And there are many ways. Even the income of your sample can be dichotomized into two. For example, you have a sample with salary of 5,000 to 10,000 salary. You also have samples with a salary of 10,001 to 20,000 all the way to 100,000. And then you're just going to say, well, based on the sample size, I can split the two, and I would just say anybody who who earn less than 30,000 or less are in grouping number one, and 30,001 and higher will be my grouping number two. And again, that is your dichotomous or two categories variable, and you can now have two independent samples. And that's typically your independent variable, but not always. And then you're going to compare the means of your dependent variable, no matter what that variable of interest is. So always remember independent variable most of the time when you group your variables, and you group them into two categories. And again, the example could be gender, immunization status, could be income, could be educational level. You just need to be curious, you just need to be inquisitive, and you need to have a good grasp of your research topic, and you start theorizing, and you start playing with your data to explore some of the results, but with a caveat that when you start exploratory findings and they are not actually stated as your objectives from the time you design your study, that is not acceptable in scientific research. You are not supposed to do exploratory, you're not supposed to do exploration of data, but you are not prohibited from exploring what ifs in your data, but if it's not part of your objectives, you are not supposed to run statistics outside of your stated objectives, stated goal, and stated plan for your research that you have submitted to the IRB. All right, measured variables. What are these? These are typically your dependent variable. These are also in the forms of interval or ratio type of data. So from the word itself, let's do a quick review. Interval are data where the distance between the values are exactly the same, and that's what we call interval data. And then the ratio is an interval form of data, but it has a natural 0 point. So that's just a quick review of what's interval and also what's ratio. So examples of your dependent variables could be the length of stay in the hospital, the age, the weight, and so on and so forth. It could also be cholesterol level. That is your dependent variable. It could also be hemoglobin level. All of your laboratory values in medicine could be your dependent variable. Cytokines, what's the IL-6, what's the IL-10, IL-1A, all of that, and so on and so forth. Those are all dependent variable, and they are interval or ratio data, and you wanted to know what is the mean of those particular data points. And then your independent variable would be that groupings, male versus female, executive versus non-executives, and so on and so forth, depending on what your literature of review would suggest that you start hypothesizing in terms of your independent variable of interest. The typical research question on a independent sample t-test is we have here on our screen. On average, will male dieters lose more weight over a 3-month period than female dieters? So we already have our two categories, our grouping variable, male and female. And what is it that we are interested in looking in terms of dependent variable? It's the weight. It says here whether they would lose more weight. So what is the weight loss in pounds over a 3-month period? Now remember, as I mentioned earlier, that independent t-test, independent samples t-test is a parametric test. So why is it parametric? Because we are using the parameters. Parameters are simply defined as features or characteristics of your population of interest. So every time you use the mean is a feature or characteristics of a known population. And that's why it's your independent samples t-test is under parametric test. It compares the means of two unrelated groups. It's parametric because it assumes a normal distribution, and remember, it utilizes the mean, and that's why there is also a normal distribution, and that is what you call parametric. That's a feature of parametric test statistics. Normal distribution is definitely attached to the concept of mean, because in order to have a normal distribution, your data must be symmetrical to the mean, because if it's not symmetrical, it's either skewed to the right or skewed to the left, and that is calculated by your skewness. So I hope that this is very clear. If it's not clear, just send me an email again. And um, you need to be able to explain to a layman's person when they say, what is a parametric test? Well, the answer when someone asks you about parametric test is to think about features and characteristics of a population. So it utilizes the features or characteristics, particularly the mean. So a mean is a feature or characteristics of a known population. And then you can follow up with the second concept, that it assumes a normal distribution, because when your data is symmetrical to the mean, and that is a feature of your population, then you know that it assumes a normal distribution. So independent samples t-test reports the mean of each group and also reports the standard deviation of each group. So that's why it's parametric. Every time you think of parametric test, it's attached to the concept of the measures of central tendency and measures of central dispersion. And the measures of central tendency are your mean, median, and mode, but in parametric it's usually the mean. And then in terms of the measures of central dispersion, it typically uses the standard deviation. So that is the key concept of independent sample t-test. It has two means from two unrelated groups. It's parametric. It assumes a normal distribution with the key concept that it utilizes the feature or characteristics of a known population. How do you know? Because it will report the mean of each group, and it will also report the standard deviation of each group. Well, what happens in Mann-Whitney U test then? As I've mentioned earlier, that it is non-parametric tests. Well, non-parametric tests are those that has no assumption about the distribution. So it doesn't use any of the principles of the measures of central tendency. It doesn't use the principles of the measures of dispersion. So, but in the same vein as your independent samples t-test, the Mann-Whitney U test still compares the distribution of the values in two unrelated groups. There's a caveat here. Although the Mann-Whitney U test technically doesn't use those measures of central tendency and measures of dispersion, which are features or characteristics of a population in a normally distributed group. Well, non-parametric tests such as Mann-Whitney U test says that it has no assumption about the distribution, but it has a caveat. It actually reports the median of each group and also reports the interquartile range of each group. Why does it report these two important values? Well, that's because that is the mathematical calculation of the Mann-Whitney U test statistics. Whether you like it or not, if you are the one who will develop a new statistical test, you have to start somewhere. Just like Gosset, when he developed the t-test, somehow you need to start. You can't just start out of nowhere. So the Mann-Whitney U test, even though it says no assumption about distribution, doesn't use features or characteristics of a population, but when you look closely at the mathematics of Mann-Whitney U test, it actually utilizes the median of each group and also utilizes the interquartile range of each group. But they claim that they are non-parametric. So here's an example here. We have a data that come from a study of 17 male and 15 female dieters to test the following null hypothesis. The null hypothesis is that there will be no difference in weight loss between male dieters and female dieters. Very simple statement. This hypothesis stems from the research question we posed earlier that says, do male dieters lose more weight on average than do female dieters? So, what are the steps of hypothesis testing for t-test? Well, number one, you state the null and you state your alternative. We already know the null, there will be no difference. The alternative, there will be a significant difference. Number two, define the alpha and state the critical value. Well, we're going to always, the acceptable alpha value, alpha level is always at a 0.05 level. So the statistical significance will be defined as the p-value equal or less than 0.05. The critical value, of course, now you need to incorporate your degree of freedom. Always remember that your t-test incorporates your degree of freedom, and that's n minus 1. So using the table of critical values in the t-table, we find the critical values that the rejection region is plus or minus, is equal or higher than 2.042. If the t-test statistics is greater than 2.042 or more negative, smaller than minus 2.042, we will reject the null hypothesis. So obviously this is a two-tailed critical value, and you need to look at your table if you don't have SPSS, but we do have SPSS now, so again, we don't need to worry about this. And don't forget that you need to know your sample size in order to obtain your degree of freedom. Number three, are the assumptions met? The grouping variable is dichotomous. Yes, it's male versus female. Men and women in the study constitute an independent random sample. So it has to be a random sample. There's equal chance to be selected as part of the study. And then weight loss data are normally distributed. Well, we will see this stem and leaf plot on the next slide to make sure that we check whether our weight loss data are normally distributed. And then the other assumption that must be met is that weight loss data are of ratio measurement scale or interval type of data. Well, for presenting the quantitative data in a graphical format that is similar to your histogram, you can actually use your stem and leaf plot. The stem and leaf plots display the relative density and shape of the data. It gives you a very quick overview of the distribution, because remember, you need to check your data whether it's normally distributed right away, because t-test is usually 30 samples or less, and you need to inspect your data using your stem and leaf plots whether you have a normally distributed data from your sample. So right here, if you look at stem and leaf plot of weight loss data, you can see on the left side you have the frequency. So there's 1, there's 6, there's 8, there's 9, there's 5, there's 2, and then there's 1. So those are frequency, the number of the sample that has the value of, and then you on the stem and leaf plot you actually put the different value and of your weight loss. So there you have 0.3, 1 has it, and then 0.5, and then that's for the total group on the top. And then for women you actually have 1 got 0.3, there were 4 who got 0.5688, and then there were 5 who got 1.023, 3 and 3 and 3, and then there were 3 who got 1.668, and based on the stem and leaf plot, So uh, if you actually mark from point 3 all the way to the 9 and then going down all the way to 3.0, that shows you that it seems like this data is normally distributed because it has a bell curve appearance. So that's the function of stem and leaf plot. Is it will give you a bird's eye view whether your data is normally distributed. Okay, so number 4 here, in terms of computing the mean and then the standard deviation for each group. So for a particular case, women had the mean weight loss over 3 months was 12.13 with a standard deviation of 5.46. For men, the mean weight loss was 18.59 in pounds with a standard deviation of 6.02. And then you have the overall mean weight loss, and you also have the overall standard deviation. So when you compute the independent samples t-test statistics, you can see that the formula is really long. We're going to skip that one. We're going to use SPSS. Basically, the next step then is to determine the statistical significance. What we got from our example is that the computed t-test statistics of 3.16 is larger than the critical value of 2.042. So what do you do if your t-test statistics is larger? You then conclude that the difference in mean weight loss between males and females is statistically significant because it's higher and therefore it is above the critical region. In short, men lost an average of 18.59 pounds with a standard deviation of 6.02, and women lost an average of 12.13 pounds with a standard deviation of 5.46. And this is statistically significant difference at a p level of 0.05 by the independent samples t-test. We're going to skip again the learning check, and we're just going to move on to paired t-test. Paired t-test is again the different examining is a test statistics to examine the difference between two related groups. Why do we say related now? Remember that the independent samples t-tests are independent. They are not related. Well, this time you are going to do the paired t-test. This is now the difference between two related groups, and this can be done when you do pre-test and post-test research design, because you actually have one person, so it's related, and you can repeat your measures using the same person, and that is why it is considered a mean from two related groups. Are the means or medians of two related groups different from one another? That's the research question when you do your paired t-test. What are two related groups? Well, number one, intervention group and a match control group. The other one is pre-test, post-test measures on the same person. That is related because it's the same person. When you do twin studies, so again, they are called two related groups. So those are examples again when you want to use your paired t-test. When you have intervention group and a match control group, so they are now paired t-tests, because even though you have an intervention group, but you also match it with a control group, so you're trying to make them similar, and so that's why you have two related groups. And then the pre-test post-test measures of the same person, because obviously you're taking your measures on the same person, so that is related. And then the twin studies. What are your typical grouping variables for your paired t-tests? Well, we already talked a while in the past slide that pre-test time and post-test time in the same person is your grouping variable. And then you can have the person and a match control that is closely related to that particular person, and that is why it's called a paired t-test, because they're supposed to be related. So what are the characteristics then when you look at the interest variable? Um, the previous slide was talking about independent variable. Now what about your dependent variable in a paired t-test? Well, examples of dependent variables in a paired t-test would be blood pressure pre and post medication, the weight for case and control, and so on and so forth. The other thing that I could think of in terms of paired t-test is actually when you do test, retest, reliability testing for an ordinal scale or a survey questionnaire. So what happens is that you give the questionnaire to your sample, and then 1 week later you repeated the same questionnaire, and that is what you call test retest. And what you're trying to do is you're trying to measure the internal consistency, that the answer of your sample is the same answer or as close as the same answer to the one that they have given you a week ago. And that's why there's a rule when you do test retest reliability of a survey, that it has to be done no later than 1 week, because obviously people can also forget what they have answered in terms of their values or their opinions or their preferences. So when you're trying to establish reliability of your survey or your ordinal scale, you can actually do test retest reliability measure. But the test statistics that you're going to use in that situation is actually the Pearson R correlation. And the higher the correlation, then the more it shows that you have internal consistency of the answers of your respondents. And that is an indication of a good, reliable tool. All right, going back here, what is your typical research question then in a paired t-test? Well, one example that we have is that, does a healthy heart education program increase the knowledge about cardiovascular knowledge in teenagers? Well, your grouping variable would be a pre-test and a post-test measure. And your dependent variable would be the score on a 100-point quiz about cardiovascular health. And your SPSS will immediately give you your t-test statistics. And if you're sure of the direction of your results, then you can do one-tailed t-test. If you are unsure of the direction of your results or your experiment, then you need to do two-tailed. And it's important to know that there are differences in the critical values for two-tailed versus one-tailed critical value. So two tests are possible. Paired t-test is parametric because, again, t-test always uses the mean and standard deviation, which are features of the population of interest. Whereas when you do non-parametric testing or non-parametric test statistics, you're going to use the Wilcoxon. I'm sorry, there's a misspelling. It's actually spelled as XON, not XIN. It's Wilcoxon Matched Pairs Test, and it's called non-parametric because again, it's not assuming normal distribution, and it doesn't use the features of mean and standard deviation. This is very similar when you think about the one sample. Um, when you think about independent sample t-test and you use it's parametric and you use the means and the standard deviation, and then you have your Mann-Whitney U test for non-parametric for independent samples. That's non-parametric. You use the Mann-Whitney U test. Well, what happened now is you have two related groups. Is two tests possible? Well, again, the answer is yes. For parametric, you do your paired t-tests that are um, for related groups. Whereas your non-parametric, you're going to use the Wilcoxon Matched Pairs Test. So, paired t-test, it compares the means of two related groups. It's parametrics. It's a parametric test statistics. It assumes a normal distribution. It uses or utilizes your mean, standard deviation, which are features of a population in a normally distributed group. And it will report the mean. It will report the standard deviation. What about Wilcoxon Matched Pairs Test? Well, it compares the distribution of the values in two related groups, just like your paired t-test, but this time it's non-parametric. It has no assumption about the distribution. It does not utilize your mean and standard deviation. But just like your Mann-Whitney U test, it has to start somewhere, and it will utilize the median of its group, and it will also report the interquartile range of each group. So I hope you remember this, that Mann-Whitney U test is non-parametric, doesn't use mean, doesn't use standard deviation, but there's a caveat. It uses the median and it uses the interquartile range, and that's for independent sample t-test. What about for two related groups? Well, you have the paired t-test for parametric, and you have the Wilcoxon Matched Pairs Test. Wilcoxon, just like Mann-Whitney, it utilizes the median, it utilizes the interquartile range in its mathematical calculation for its significant statistical value. We're going to skip again this learning check, and let's look at this example data from a study of 31 teens using paired t-test. The teens took a cardiovascular health quiz before attending a healthy heart program and took the quiz again after completing the program. The null hypothesis: there will be no difference between the pretest and the post-test cardiovascular knowledge. Alternative hypothesis would be there will be a significant difference in cardiovascular knowledge after attending the program. Of course, this hypothesis stems from the research question: does a healthy heart education program increase the knowledge about cardiovascular knowledge among teens? You define your alpha level, you look at your critical value again in the table, and then you know that you need to define your rejection region. For two-tailed test, again, it's equal or higher than 2.042, plus sign, or less than 2.042 for the negative direction of your study. And because it's a t-test, you need to look at the degree of freedom again. You look at your table, but in SPSS, you will just get your t statistic value immediately. You must ensure that the data meet the assumption. There are two paired. It has to be paired. Do not ask whether you can still use data that you haven't paired correctly. You cannot use. It will violate the assumption that these are paired measures of the dependent variable from a related group. And related, it's related because you're taking it from the same person. If you mix and match your pre-test and post-test results from your different participants, then they are not considered paired measures anymore because they are no longer from related groups. The data are approximately normally distributed, so you can check the stem and leaf plot on the next slide. So you can see there, again, you just mark from 4.8 all the way to the 4 and then all the way to 8.8 down there, and it looks like it has a normal it looks like a bell curve, but it's flatter. Remember, that's the feature of a T distribution. And so again, it's just a very simple indication that it's just for you to have a bird's eye view whether it's normally distributed, because that's one of the assumptions of a t-test. You compute the mean, and this is the results, a pre-program and a post-program. Again, this is the paired t-test statistics, very complicated, but SPSS will calculate that for you. Since our computed t-test statistics was minus 6.935, which is smaller than the critical value of 2.042, we conclude then that the difference in test scores from pre-test to post-test is statistically significant. Because remember, this is minus 6.935, and anything below minus 2.042, according to a two-tailed test, then it is statistically significant. So how are we going to say this when we publish our result? Well, we're going to say it overall, the post-test score was an average of 9.03 points higher than the pre-test score, and this was significant at a p-value, at an alpha value of 0.05 by the paired t-test statistics. We can conclude then that the teenagers in this sample had significantly higher test scores after going through the educational program. We're going to skip the learning check, and actually that is the end of this video, and we're going to talk about ANOVA on a separate video.